non-compact hyperbolic three-manifold of finite volume. M will always be a surface of finite area with a hyperbolic metric that's complete. And what we're going to do is look at surfaces in N and in M cross S1 with the product metric space. And I'd like to convince you that the study of properly immersed minimal surfaces and constant mean curvature surfaces in these spaces is interesting. There's been very, very little work on minimal surfaces in these hyperbolic three manifolds. In M cross S1 as well, there's not a great deal of work. In fact, for these kind of surfaces, M2, I know of nobody else who's looked at this problem. And I'll tell you what we've been doing for the past 2 years. Now, I'd like to make some comments on what these manifolds are we're looking at. If I ask people in this room to give me an example of a surface M of finite area, the metric of curvature -1, that's complete, then after a few minutes you'll come up with the first simple example, which is a three-punctured sphere. And I mean, it's just, I think everybody in the room who does a little geometry will just come across this example naturally. In the hyperbolic plane, take an ideal triangle, reflect about this side. So now we have a quadrilateral. And consider the hyperbolic isometry, which is parabolic translation about this point A. The other hyperbolic isometry, which is parabolic translation about this point B. And identify the union of these two ideal triangles with these identifications on the boundary. And you'll get M, which will be S2 minus 3 points, with a hyperbolic metric of curvature -1 and area 2 pi. And the ends have a nice geometric structure, which we call two-dimensional cusps. If I take a horocycle here, then the point here is identified with this point here. So what you see in the quotient is a cycle here, which has intrinsic curvature 1 on the surface, and these horocycles here are shrinking down in length exponentially. This is called a two-dimensional cusp. And we see this here. This is identified with this. We have one more cusp here, and we have another cusp here. So here there's three ends. Each one is a two-dimensional cusp. Let me just mention for reference that if this horocycle here has length equal to c, then the area of this piece is also c. A little remark I'll use later. And then if you want to say, okay, what are the other m's? Then you'll develop a moduli theory of Riemann surfaces. You'll talk about a four-punctured sphere. You'll talk about a torus with punctures. And you'll talk about a surface, a compact surface with n punctures. And you'll talk about all possible metrics of finite area of curvature -1. And that's Teichmuller theory. But if I ask you the same question about a three-dimensional manifold, probably there's not more than two people in this room who can give me one example. Let me just ask a question. Can anybody in this room give an explicit example of a manifold n, sectional curvature equal to -1, complete in a finite volume, non-compact? Misha can. Two people? Very good, two people. Anybody else? Okay, so I'd like to spend a few minutes talking about these manifolds and try to convince you that it's really interesting to look at them and do surface theory in these manifolds. So in 2 dimensions, we saw the simplest example possible. I mean, you come across that if you try and work. And its area is 2 pi. Any other such example, M, has area strictly greater than 2 pi. This is unique with that area. So you can ask yourself the question, well, let's look for n and ask ourselves the question, what's the simplest one? And is its volume unique? Does it classify the manifold the way 2 pi here classifies the manifold, et cetera, et cetera? Okay. So the simplest example I know of is obtained by taking a regular tetrahedron in hyperbolic 3 space. It's convenient when you draw pictures here and work on a blackboard to work in the Klein model. So I take the unit ball and think of the metric of curvature -1 in the Klein model, but you can just as well think in the Poincare model for what I'm going to do. And take T to be a regular Euclidean tetrahedron with 4 vertices on the unit sphere, so 4 ideal vertices, and dihedral angle pi/3. You can convince yourself you can construct such an example. Those 3 points, the 4 vertices are at infinity on the unit sphere, and that's a regular tetrahedron in H3. And I'm going to use this throughout the talk to give examples. So let me just so this dihedral angle here is pi/3. They're all pi/3. And these points are at infinity here. And that's this regular tetrahedron T, inscribed in the unit ball. Okay? There are 4 faces there, A, B, C, D, which I'm going to need for further reference. A is this one, B is this one, C is the back face here, C, and D is the bottom face here, D. Now, the manifold N in question is going to be obtained from this tetrahedron by identifying the faces. I'll identify 2 of the faces, A and B, and 2 of the faces, C and D. How are we going to identify A with B? We'll do a rotation by 2 pi/3 about the top vertex V. Here's V. I'm going to identify this face with this face by rotation by 2 pi/3 that takes this face to this face. So this point will go to this point will be identified with this point, a point here with this point, etc. A point here with this point. That's the way we identify A with B. So we take this tetrahedron T and identify A with B by that rotation by 2 pi/3 around V. Now I want to identify C with D. Well, look at this vertex here, W, and do rotation by W by 2 pi/3 to take C to D. So a point in the back here, for example, a point here will go to a point here. This point will go here. This point will go here, etc. Okay? So identify the face A with B by rotation by 2 pi/3 about V. C with D by rotation about W by 2 pi/3. Think about the quotient. This quotient has 1 vertex at infinity. It's not in this space because all the vertices are identified. 2 faces and 1 3 cell. The 2 faces are the faces that come from identifying A with B and C with D. That's 2 faces in the quotient. And there's only 1 edge in the quotient because this point is identified with this point by this rotation, which is identified with this point. Now I rotate around W. This point goes here, and then this point goes here. So there's 1 edge. Now, why is this manifold a hyperbolic manifold? Why do we have a hyperbolic structure? Well, there's no vertices to worry about. They're all in infinity. The only thing to worry about is what happens at an edge. But if you think about it, at an edge, you have 6 faces coming into the edge at angles pi/3. So that means 1, 2, 3. Well, it's not very symmetric. You can do better than that. So this face is coming into this edge. Here's the edge. This angle is pi/3. It continues smoothly across the other side. We go around once and we close up 2 pi. So a neighborhood of that point on the edge is a ball in hyperbolic 3 space. So this manifold is a hyperbolic 3 manifold. Why does it have finite volume? Well, let me make one remark about this manifold here. So call this manifold for the moment, it'll be N. This manifold is not orientable. The link of the vertex V is a Klein bottom. and it's not hard to see. Here's the vertex V. Think of a horosphere intersecting this tetrahedron. You'll see an equilateral triangle here in that horosphere. That's a Euclidean equilateral triangle, angles pi over 3. And you're going to glue together these triangles by the identifications on the sides that you get. You see it's a Klein bottle. So there's one end in this manifold. It has finite volume. You can calculate it explicitly. And that's the manifold N I'm talking about. It'll come up today quite often. One of the chapters in Thurston's book on this subject concerns the two-sheeted orientable covering of this manifold. The orientable two-sheeted covering. This is chapter 5 of his book. And this is the three-sphere minus the figure 8. So, can I draw a figure 8? So this is over, under, figure 8. The three-sphere minus the figure 8 topologically is the oriented two-sheeted covering of this manifold. This particular manifold has been studied quite a bit by Thurston, Riley, and Jorgensen. And Riley and Jorgensen used arithmetic methods to prove there's a hyperbolic structure on the manifold. This is a proof that there's a hyperbolic structure on the manifold. This manifold N here was discovered by Giesekind in 1912. I don't think Thurston knew about this manifold because, I mean, he would have mentioned it. It's just so easy to come up and much easier than the way he introduced the figure 8 knot complement and obtained this hyperbolic structure. So I think he just didn't know about this. Adams proved that this has the smallest possible volume, it's approximately 101, among complete hyperbolic manifolds of finite volume. So the Unicity Theorem here, analogous to the theorem of a three-punctured sphere. The oriental two-sheeted coverings, the complement of the figure 8 knot, and as I said, Jorgensen and Riley proved that has a hyperbolic structure of finite volume. There are two structure theorems that are important which say why these manifolds N that I'm talking about are particularly interesting. The first theorem is by Jorgensen. It says that take any volume V, there are a finite number of complete non-compact hyperbolic 3 manifolds with volume less than or equal to V. Only a finite number. And then the theorem of Thurston that says any compact hyperbolic manifold of volume less than or equal to V is obtained from one of these finite number by doing hyperbolic den surgery. Hyperbolic den surgery is considering the manifold N. An end of N is a cusp end. It's a 2 torus cross R plus. And hyperbolic den surgery means you take out the non-compact end of that and you glue in a solid torus by a certain diffeomorphism of the 2 torus. And Thurston studied this process of creating hyperbolic structures on 3 manifolds, hyperbolic den surgery. So understanding these finite number of n's for any volume V is, in a sense, at least topologically understanding compact hyperbolic 3 manifolds up to this den surgery process. So these are interesting manifolds. Let me make a remark about what the end of these manifolds N are. I just said it in words, but explicitly, you consider the half space, or the end will be just y greater than equal to y0. The metric is the hyperbolic metric, the Euclidean metric divided by y squared. And the group is a group of parabolic transformations leaving the plane xt invariant. So for each y, no, leaving the y equals constant invariant, which is the plane xt. So what I'm doing is taking in this model here, I'm taking a half space. This is y, x, t. I'm thinking of this half space here as h3 with that metric written down there. The hierospheres here are the planes y equals constant. Y is equal to y0. So the end is everything after this one. I'm quotienting this by some group of Z2 linear transformations. So, for example, translation in X, translation in T. That gives a torus here. And in the quotient, what you see is, so this is really the geometry of the cusp n in the quotient is a cusp of this sort. Metrically, you're seeing here a torus. So this is, say, T of y0. This is T of ys. T of y. You go a distance s along the geodesics. And the T of y here are shrinking down exponentially. The metric is shrinking down exponentially. So here, a length here, when you go a distance s along the orthogonal geodesics, gets shrunk down by exponential s. And that's a standard cusp end. So this is a torus, but in the induced metric, that torus has a Euclidean structure. It has mean curvature 1. The mean curvature vector here has length 1 for each of these tori. So this end here is foliated by these constant mean curvature 1 tori. And in that end, we have the surfaces which take a geodesic of this torus, so it's just a straight line quotient in this flat torus, and take that straight line, cross R+, and that'll give a two-dimensional cusp. So I take a geodesic of T of, say, y0 cross R+. That's a two-dimensional cusp, as we described here. Okay, so that's some information. I won't talk about M cross S1. So the main theorem, perhaps, that we proved concerning these spaces and minimal surfaces is the following. Consider a finite topology, properly immersed, orientable minimal surface, sigma, in N or in M cross S1. Then it has finite total curvature, and it's equal to 2 pi times the Euler characteristic. So any finite topology, properly immersed surface in one of these hyperbolic manifolds, or in one of these manifolds M cross S1, one understands the geometry. The ends are asymptotic to standard models. In the hyperbolic manifolds, they're asymptotic to those geodesics cross R+, the two-dimensional cusp ends. And in M cross S1, there are 3 models. But I'd like to concentrate today on the hyperbolic case. Okay, so this is the main theorem. I'd like to talk about this theorem, applications of it, and other theorems in the subject. Okay, wait, let me go back for a second. When you start doing geometry like this in certain spaces, you also say, well, what about constant mean curvature surfaces? And you ask yourself the question, is there a Hopf theorem? Is there an Alexandrov theorem? A Hopf theorem, for example, says that in R3, an immersed constant mean curvature sphere is a round umbilical sphere. So you can ask yourself that question in these manifolds N and in M cross S1. In N, that question has an easy answer for the following reason. The universal covering space of N is hyperbolic 3 space. So if I take an immersed constant mean curvature sphere in N, I can lift it up to the hyperbolic 3 space. There it's a round sphere. So when I project back down, I have an immersed umbilical sphere. So the Hopf theorem is trivial in these manifolds N. However, fortunately, there's very interesting things one can say if one talks about constant mean curvature surfaces different from spheres. For example, the most simple one after the sphere is the torus. And there we have a very nice theorem which says the following. It's even more general. This is a theorem that I proved with Laurent Mazet. Consider a complete Riemannian 3 manifold with sectional curvature less than or equal to -1. Let T be a constant mean curvature 1 torus embedded in X. So I'm taking a constant mean curvature torus of mean curvature 1. Theorem, T separates X, and its mean convex side is isometric to a hyperbolic cusp. So the torus is exactly equal to one of these T of Y's And the mean convex side in this manifold X is a hyperbolic metric, curvature -1, isometric to this. So it's a rigidity result in the style of Hopf's theorem. An embedded constant mean curvature 1 torus, you have this rigidity. Well, the hypothesis is sectional curvature less than or equal to -1 and complete. Let me just mention that Massey and I proved more. This comes from an unpublished paper of Calabi. Calabi looked at things on surfaces. Suppose you take S2 with a metric of curvature between 0 and 1. Then it's not hard to see that if you take a simple closed geodesic, its length is at least 2 pi. So this unpublished paper of Calabi proved that when the length is equal to 2 pi, then the surface is isometric to the unit T2 sphere or to S1 cross R, a cylinder. So we asked ourselves the question, well, what about dimension 3? Is there an analog of this in dimension 3? And here's the theorem. Suppose M is a complete 3-manifold whose sectional curvatures are between 0 and 1, and you take a minimal embedded 2-sphere in M. Then the Gauss equation implies its area is at least 4 pi. If the area equals 4 pi, then you have rigidity. If the area equals 4 pi, then the manifold is isometric to the unit 3-sphere or to a quotient of S2 cross R by an obvious group of isometries, which I wrote down there. So the existence of a minimal sphere of this area gives you rigidity under these hypotheses. Okay. Let me make some introductory remarks about these surfaces N, these manifolds N, to understand what I'm doing in minimal surfaces. In three-dimensional topology, when you have incompressible surfaces, then you can begin to understand the topology of the manifolds. And Haken studied manifolds that are irreducible, which means every 2-sphere bounds a ball in the manifold, which contain non-trivial incompressible surfaces. And nowadays they call these things Haken manifolds. And he obtained invariants of knots and links in manifolds of that type, irreducible and always containing incompressible surfaces. He was able to cut along the incompressible surface, obtain another manifold, and keep on cutting along successive irreducible surfaces until he arrived at a ball. And using this, he was able to define invariants of knots and prove very nice theorems. And for a long time, people thought that any irreducible 3-manifold was a Haken manifold, except for some cyclist vibrations. And Thurston discovered many hyperbolic link complements of links in S3, which indeed contain no incompressible surfaces after you make them compact by doing dense surgery. So these manifolds had no incompressible surfaces. Now, if you take a manifold N like this and you take a totally geodesic surface in there, it's necessarily incompressible. You can think about that for a few seconds, do a little geometry to show that the fundamental group of any totally geodesic surface in such a manifold N goes in injectively. So you can ask yourself the question, well, can I find totally geodesic surfaces in these 3 manifolds N? There's an incredible literature on this subject. I was very surprised to discover this a few months ago. Many people have written many papers on totally geodesic surfaces in these manifolds N. Unfortunately for me, almost all the papers, with some exceptions, concern arithmetic groups. They look at subgroups of SL2C that come from arithmetic, and they prove that totally geodesic surfaces exist or do not exist because they're looking at for Fuchsian subgroups. And hardly ever do they discuss the question of whether the surface in question is embedded, immersed, or even proper. So for me, this is a very difficult subject to learn from, because when you look at that paper and you try and answer the question, it's very, very difficult. Let me just mention, if I take a manifold N like this, when you consider the universal covering space H3, if I take any point in any 2-plane, I have a hyperbolic two-plane through that point in H3. So I can just project down. I get an immersion of totally geodesic in n. So any point of n and any two-plane of n, there is an immersed totally geodesic surface through that point. But is it compact? Is it embedded? Is it proper? Is it immersed and proper? I mean, that's the question. But let me just mention some of the theorems in this subject. Milson constructed infinitely many closed hyperbolic n manifolds that have embedded totally geodesic hypersurfaces. So they do exist very often. There are infinitely many hyperbolic knot complements that contain no closed totally geodesic surfaces and do contain non-compact such surfaces. Gordon and Littleland, the complement of the figure 8 contains many closed totally geodesic surfaces. There's no embedded example. So in the complement of figure 8, there's no embedded totally geodesic compact surface. There's the reason for it, but perhaps I'll not go into that for time. There's one very pretty geometric theorem that's inspired me to look at some stuff of atoms. Any incompressible proper embedding of a three-punctured sphere in n is isotopic to a proper totally geodesic embedding of the three-punctured sphere. So if you can find a proper embedding of a three-punctured sphere, then you can find a totally geodesic one isotopic to it. And this is very, very interesting for knot theory, at least hyperbolic knot theory, because many knots you can draw and you can immediately find incompressible three-punctured spheres. For example, if I take a knot of this nature, okay, so I claim there's an incompressible three-punctured sphere in that picture, which is just this disk. You should think about why in heaven's name that's a three-punctured sphere. So this picture should be a little improved. There are the punctures. 1, 2. It's a disk with two punctures, and a disk with two punctures is a three-punctured sphere. That's incompressible, so it's isotopic in the complement to a totally geodesic three-punctured sphere. Why is that interesting for doing geometry and topology? Because you can cut and paste. You cut by this totally geodesic three-punctured sphere. You take some automorphism of it, and you reglue. You get a manifold with the same volume, which is non-isometric to it. So you can do many different things with these kind of totally geodesic surfaces. So my point of view is now do minimal surface and constant mean curvature surface theory in n and prove theorems of the nature we've just seen. Understand what's going on. So let me just give some applications, first of all, of this finite total curvature theorem. Here's the theorem. A finite topology properly immersed surface in n has finite total curvature equal to 2 pi times the Euler characteristic. So some applications of that. When you look at this theorem with the Gauss equation, it gives topological obstructions for the existence of proper minimal immersions. For example, a plane cannot be realized in n or in m cross S1. There is no proper minimal immersion of R2 into such a manifold n. An annulus can never be properly minimally immersed in such an n. If it's immersed properly in m cross S1, then necessarily it's equal to a geodesic of m cross S1. So you have a classification theorem. Why? Well, what's going on here? When you look at the Gauss equation, the finite total curvature equal to 2 pi the Euler characteristic gives you this equation here. Okay? That's the extrinsic curvature, the sectional curvature. Since it's minimal, this is less than or equal to 0. That's between -1 and 0. In n, it's -1. So immediately you get that 2 minus 2g minus n is less than or equal to 0. And if you have equality here, if this is 0, since this is less than or equal to 0 and this is less than or equal to 0, they're both 0. So equality here means the extrinsic curvature is 0 and the sectional curvature is 0. Here. So for example, a plane. Why can't you minimally immerse a plane? A plane is G is 0 and n is 1. But G is 0, 2 is less than or equal to n cannot be 1. So a plane can't be minimally immersed either in m cross S1 or in n. What about an annulus? An annulus is G is 0, n is 2. Well, 2 is less than or equal to 2. That's possible. But since you have equality, the extrinsic curvature is 0, sectional curvature is 0, so it's not possible in n. You can't do it in n. And if you can do it in m cross S1, since the extrinsic curvature is 0 and the sectional curvature is 0, the tangent plane is vertical, and you can prove it's a geodesic cross S1. So this theorem immediately gives these classification theorems like this. Oops. In n, you have an area estimate that comes out of this equation. The area of the surface is less than or equal to 2 pi 2g plus n minus 2, and equality means it's totally geodesic. Okay, existence results. So this is the work that I find very interesting. Consider such a manifold n. Okay, you'd like to know when can you find embedded minimal surfaces of a given topology in n. There is a properly embedded minimal surface in n of finite topology. It's incompressible, stable, and not compact. So one has this existence theorem in these manifolds n for properly embedded minimal surfaces, non-compact. Now the idea is to take an embedded incompressible surface in n, which one can find in n, and isotope it to an area minimizing surface. Now, this is difficult because these manifolds n are not mean convex in infinity. If I take a big geodesic ball in n, it gets into the cusp end, and the cusp end is foliated by these mean curvature tori here, where the mean curvature vector is going out. That's the mean curvature vector. So this is not convex, mean convex. When you want to solve plateau problems, you want to minimize area, then if you take a minimizing sequence, there's no reason why that minimizing sequence won't disappear to infinity. I mean, I could take some surfaces here whose area is going down, going down, going down, and maybe the area goes off to infinity when you go to the minimum. So solving plateau problems here is not obvious. This theorem in particular says that in the complement of the figure 8 knot, one can find a minimal torus that's embedded. Now here's a theorem that we proved in collaboration with Laurent Mazet. Recently Laurent Mazet has started working with us, which says that you can find a compact embedded minimal surface in any such n. Now this was something that was not obvious to me at all. How in heaven's name can you find a compact embedded minimal surface in any such n? One way to try and find it is if you could find a compact incompressible surface, you could try and minimize area in the isotopy class and hope it doesn't escape to infinity. You can try that. But Thurston proved that there are compact hyperbolic 3 manifolds that contain no incompressible surfaces. They exist. So you can't do this by looking for incompressible surfaces. What can you do? Well, you can try minimax techniques, and it works. Let me give you an example of the minimax technique in the simplest possible case, and just perhaps I'll stop there after that. Let's take this torus T here and try and construct here a compact embedded minimal surface. And that compact minimal surface will lift up to a compact embedded minimal surface in the figure 8 knot complement. The surface here we're going to construct is going to be a genus 2 surface plus a connected semi-projective plane. When you lift it up, it'll be a orientable genus 3 compact minimal surface in S3 minus the figure 8. But this is true in any such n. Using minimax techniques, we've managed to prove it. But I think it's interesting to give this example this particular example to appreciate what's going on. Let me mention that, okay, so let's see what's written down here. One does a minimax construction and proves the solution does not enter the cusps. So look at the theorem that's stated there. T1 is a polyhedral tetrahedron in hyperbolic space, some of whose vertices may be ideal. There's an embedded minimal disk D in T of 1, whose boundary meets the boundary of T of 1 orthogonally, meeting each face in at most one connected curve. So I take some tetrahedron, not necessarily an ideal tetrahedron, in hyperbolic space. So these faces are totally geodesic. This might be an infinity. This might be in the space, P, Q, R. And I claim that there's some improperly embedded minimal disk there that you can get using minimax techniques, which intersects the boundary orthogonally. So this face, it meets it like this face meets like this face like this, like that. There's the using minimax techniques and studying why the minimax solution won't go into the cusp and disappear at infinity, one can prove this exists. Okay, so let's assume that theorem and see why we can construct a compact embedded minimal surface in this space. So I have a regular tetrahedron, which in the Klein model, all the vertices are at infinity. So let me now draw this regular tetrahedron like this. I draw an equilateral triangle. And another perspective on this. That's the regular tetrahedron in hyperbolic space, in the unit ball, say. Now, this vertex here at infinity, I can draw the geodesic that goes from here and minimizes distance to this hyperbolic plane. Okay? The geodesic that goes here minimizes distance to this hyperbolic plane. Since this is a regular tetrahedron, if I do this for each vertex, draw the geodesic that goes from here to this hyperbolic plane, that'll intersect this in a certain point. They intersect. And they all intersect in the same point. In other words, there's a point here, P, which is essentially the middle of this geodesic. All of the geodesics from this point to this face that minimize distance pass through P, etc. So that's this point P. Now I'm in the bottom face here. This is in the bottom face at Q. I draw the geodesic that goes orthogonal to this geodesic here. This is orthogonal. And now I consider this tetrahedron, hyperbolic tetrahedron. T1. T1. Let me try and make a better picture, exaggerate this picture better here. Okay, that's T1. Now, if you think about the fact that this is regular, if I do the reflection in the faces of T1 here, I'm going to tessellate T. 24 copies of T1 tessellate T by reflection in the faces. You could think about that. So this point here is at infinity. The other points are finite points. But I have a solution to the free boundary value problem in T1. Think of applying this for T1. So I have an embedded minimal disk here, which doesn't pass through infinity. It intersects this face in the bottom orthogonal here. It comes up here like this, comes here, comes here. I have that embedded minimal disk in T1. Now I look at this face here of T1, and I do the orthogonal reflection through this face. This disk goes to this tetrahedron here. This continues orthogonally here. This continues orthogonally here. Keep on going, all around. In other words, if I do the bottom triangle here, think of the bottom triangle. This bottom triangle, here's the point in the bottom. These all pass through the same point. Here's what I just did, this curve here. When I go around, I'll just continue this and get a closed curve on the bottom. This will close up on the bottom. This will close up here. Now, since everything is perfectly symmetric, when I do the symmetries, orthogonal symmetries in all the faces, I'm going to get a surface here, and a surface here. In other words, now this is difficult to draw. Usually you see this in a cube. In a cube in R3, this is the Schwartz p-surface. This surface here, nobody's ever thought of doing it for the following reason. A tetrahedron does not tessellate R3. So nobody thought of trying to make a minimal surface in tetrahedron like this, orthogonal to the boundary, and then taking symmetries in R3. Doesn't work. But it does tessellate, T does tessellate H3. This really surprised me, but it's true. T tessellates H3. When you take this regular tetrahedron, do all these symmetries by the sides, you get a tessellation of hyperbolic 3 space. Now this surface here, when you think about doing this, it's very hard to imagine. So this is my regular tetrahedron. What does the surface look like? Here I have a closed curve. On each face I have a closed curve. And here's a closed curve on the back, closed curve here. And they're all joined by these sort of necks. I mean, it's easier to imagine in your head than to make the picture. By construction, this curve here, when I do rotation by 2 pi over 3, I'm going to get, it'll be invariant under this group here. Rotation by 2 pi over 3 around B, rotation 2 pi over 3 around W. Back face here, this face A and B. So this curve here that we'll get here will go to this curve here, so it passes to the quotient. The curve that you get in the back goes to this curve here when you do this rotation. So it passes to the quotient. So this surface is really an embedded minimal surface in this hyperbolic 3-manifold N. And if you look at the topology, it's the surface of genus 2 connected some projective plane. And you can lift it up to the complement of the figure 8 nut to get an embedded minimal surface of genus 3 that's orientable. And one can do this in any of these manifolds N using minimax surfaces and proving that the minimax surfaces don't enter the cusps. Since they're not area minimizing, you have to think about why this is true. But this is a delicate part of the discussion. That's the theorem. Okay, thank you very much. Stop there.